This video focuses on nuclear magnetic resonance spectroscopy, or NMR, which is discussed in Chapter 15 in your textbook. The learning goals for this chapter include understanding the basics of NMR, instrumentation, and just spectroscopy itself, learning how to read and analyze the different spectra, and then using them to predict different structures and then combining them with other data. This video specifically focuses on carbon-13 NMR, so we don't go too much into the basics of the instrumentation. However, if you need to go back and review those videos, please do so because we use some of those concepts in this chapter. So carbon-13 NMR is specifically focusing on sections 11 through 13 in chapter 15. So since we're still doing NMR, it's relatively familiar to what we talked about with proton NMR. So again, if you haven't watched those videos, you're going to want to go and review those because we're using the same types of concepts here. Obviously, there are differences, but there are a lot of similarities. So some of the similarities include the same experimental theory. So you still have nuclei that spin because they have the protons that have a charge. So they spin, they create their magnetic field. When they're placed inside of an applied magnetic field, the spin can flip and then the relaxation can be measured and then you can plot it. The electrons that are also spinning around the nucleus can either shield or deshield the nucleus and affect the frequency of the flip and relaxation and where you would see it. Both proton NMR and carbon-13 NMR are plotted in the same way, so you'll still have intensity on the y-axis, you'll still have the chemical shift in parts per million on the x-axis. The chemical shift still corresponds to how shielded or deshielded the applied magnetic field feels to the atom, so deshielded is still downfield or to the left, shielded is to the right or it is upfield. The number of signals that you see are still going to be the same types of peaks. Or signals, they still go up and down. The number of signals still applies to the number of different environments. So the number of signals you see still tells you the different types of carbon-13 atoms. Again, looking for symmetry is going to be really helpful in figuring out what types of symmetry you have or what types of molecules you have. And then just like with proton NMR, there are predictable chemical shifts for certain functional groups. So just like I predicted or gave you a shift chart. Sorry, I don't want to say the wrong name there. If you have a shift chart for proton NMR, you also have a shift chart for your carbon-13 NMRs. If you notice over here on the scale, it actually gets quite a bit bigger. It's not just 0 to 12 anymore. So that leads us into some of the differences we'll see between proton NMR and carbon-13 NMR. So some of the differences, one of them, like I said, is that you have broader signals over a broader signal range or over a wider range. So for proton NMR, it was 0 to 12 ppm usually. For the carbon-13 NMR, you'll usually see from 0 to 220 ppm just because of the nature of the molecule. Some other things that are actually kind of nice and makes it a little bit easier to interpret is that carbon-13 signals actually do not split. So you're not going to see peaks or peaks within your signal like doublets, triplets, septets. That just doesn't happen with carbon-13. And the reason it doesn't happen is because only about 1% of all carbon atoms are actually the isotope of carbon-13. So there's a low probability for one that I can track a carbon-13, and then the probability of the neighbor also being a carbon-13 that's able to split my carbon-13 is very, very low probability. So if there aren't the probability of finding a carbon-13, you probably won't see the signal split by neighboring carbons. So that means each type of carbon-13 is only ever going to show up as a singlet. You'll only see one peak. For that same reason, carbon-13 signals are not integrated. So you actually can't use the intensity or the height of the peak to figure out the number of carbon atoms. There's no correlation because if only 1% of the atoms are at any given time probably going to be carbon-13, it's not enough confidence or not enough secure measurement to say how many carbon-13 atoms you have. Because you get such a low signal or you have such a low probability of having carbon-13 atoms, the signal is actually quite low. So the computer system or software is actually there have been developed these techniques to kind of scale up the signal to make it look larger so we can actually see it. When you do that, you actually increase that background noise, so you might see some background noise in there. Another thing you might see that's new is, although we still use TMS as our reference, you might also see another solvent peak show up, and usually it just looks like 3 straight up and down lines at around 80 ppm. Those are some of your main differences. So actually, let's look at one of the carbon-13 spectra. So this is what they look like. Again, it looks a little more simplified. So you still see the chemical shift in parts per million. Here you see the scale going from 0 to roughly 220. You still have your intensity up the side. Here, this is actually giving you the exact shift location. So if I'm at 180.4, that's my chemical shift. Notice that each one of these peaks is actually a singlet. I don't see any splitting, and they look very, not very intense. And then this is what I was talking about, the jagged edges where you don't actually have your background being nice and smooth. You see that enhanced background region. Some other features to look for is, because you can't split those peaks, they had to come up with a way to kind of discriminate between those different signals. And one of those things is called a distortionless enhancement by polarization transfer, or it's called a depth spectrum, DEPT. Essentially, what it does is it looks at the splitting that may be interacting with protons and carbon atoms, because those can potentially split. But here they're doing it in a controlled environment in order to figure out what the splitting is. And instead of seeing splitting, they actually just get different types of signals that behave in predictable ways depending on how many carbon atoms are actually attached to the C. So that can tell you, do I have a CH3 group, do I have a CH2 group, do I have a CH group, or do I just have a C by itself? Depending on what happens or what you see, you can kind of figure out, okay, I know this is a C signal from a CH2, or I know this is a C signal from just a C by itself, no H's. So the depth 90, how that works, when this signal or when this modification is made to the RF frequency that's applied, the only signals that actually appear in this spectrum are CHs, and these appear in the up direction, so they appear above the line. Then another type of modification you can do is run something called a depth 135, and in this case you can pick up CH3, CH, and CH2 signals, and then you actually can tell the direction. So CH3 and CH signals are in the up direction, and then the CH2 signals are in the down direction. If you have C's without any H's, they only appear in the main spectrum, not the depth. So what you could do is actually stack all 3 of them. So if you do all 3 spectra, you can stack them. If it doesn't have a label, or it's called broadband, that just means it's looking at all C's, none of this fancy modification with the depth 90 or 135. Then the depth 90 and 135 would be indicated based on what you see. So in the broadband, you should see all the peaks. In your depth 90, you should only see your CH peaks, and they should be in the up direction. And then in your depth 135, you can have peaks pointing down, or you can have peaks pointing up. And then the peaks pointing up are going to be your CH3s, and then your peaks pointing down are going to be your CH2s. And then if you have something pointing up in both your depth 135 and depth 90, that tells you you have your CH. So let's actually go through the process of analyzing the sample spectrum I have here for you, so you can kind of see how to use all 3 together to get your information. So in this case, I want to determine the structure of an alcohol with the molecular formula C4H10 that exhibits the following C13 NMR spectra. So from this, I can first determine how many environments I have, just like I did with proton NMR. If I look at the bottom spectrum, that's what I'm actually going to use, because that includes all of the C's. It doesn't look at, do I have a CH, do I have a C without anything. It just says how many different C environments do I have in the red spectrum on the bottom. If I circle all of those, that tells me I have 4 different C environments, because I have 4 different singlets that are showing up. After I do that, I'm going to analyze the depth 90. I notice I don't have any singlets in there. I don't have any signals at all. So that tells me that I have no CH groups in this structure. So if you're missing a signal somewhere, that means it doesn't exist. in that type. Then if I wanted to analyze my depth 135, if I have the inverted or the down peaks, that tells me I have CH2s. If I have the upright peak, that tells me I have a CH3. So in this case, I have 3 CH2 groups and 1 CH3 group. So then if I wanted to draw out the spectrum, I have 4 carbons in my chemical formula. I have 4 different carbons. I could also use my ppm to help me decide. So I have something that's quite downfield. If I check my list, that actually corresponds to being attached to an OH group. So then I can say that this is my signal, my CH2 that is connected. Oh, my H's got erased, but these should have H's here. So the C that's attached to the OH corresponds to the most downfield signal. And then as I get away from that OH, my signals start to have a more shielded effect. So then each step away, it corresponds to the next thing in the spectrum. So that would be the process to analyze to end up at the structure. So then if I wanted to draw this out nicely, I would have something like this. Let's do another one. So this is also for the molecular formula C4H10O, but notice that the spectrum is a little different now. So then that means I can predict a different structure, and it should look different than the one I already predicted. So I'm going to go through the same process that I already did. So this one actually has the name broadband decoupled, so that means it's just telling you that you have all of the C environments shown up. You're not doing any fancy modifications to see what H's are bonded to them. So first, if I analyze, that tells me I have 3 different C groups. Another thing I wanted to point out is notice how the stack is going in the opposite direction. Either direction is fine as long as you can read those labels and see and know what that spectrum means. So I have 3 different C environments. Then if I wanted to, I can analyze my depth 90. This tells me that I have a CH environment. And then if I analyze my depth 135, this tells me that I have a CH2 because it's inverted. And then this confirms that I have a CH3 straight up. And this confirms that I have a CH because it's an up in all of the 3 spectra. So that means I can easily identify that I have CH2, CH, and CH3, and I have 3 different environments. So then that means that something has to appear in the same environment, depending on what it is. I have something that's very downfield, so that tells me it's probably connected to the alcohol group. So then I probably have a fragment that looks like this, CH2OH. Then if I start getting away from that, I also have something with a CH and then CH3s. So if I have a CH, potentially that could go here, and then CH3s always have to go on the end, so maybe they're the ones attached in this position. So if I check this, I have CH3, I have a CH, and then I have a CH2, the CH2 being connected to the OH group. So if I wanted to draw this one nicely, this structure would probably be the best match for the spectra that I'm provided here. I have my 4 C's, my H's, and then I have everything bonded according to what's here. Notice that the integration, there is none, so that didn't help me. I had to kind of piece these together based on what those different parts per million values were. Let's do one more example. So in this one, I gave you something different between C4H10 or H8O, H10 and O. Sorry, I just wanted to show you the difference. Notice this is just my straight branched butanol, and then here I have my branched group here causing that difference. So you can see the difference in the spectra is reflected in the difference in the shape. Okay, so let's do this last one. I have C5H10O. It has these 2 different spectra, and the depth 90 spectra has no signals, so I just left it out. It's been omitted. So then immediately from this sentence, this tells me that I have no CH groups because CH is directly reflected in that depth 90, and that's the only thing that shows. The next thing I want to look at is how many carbon environments I have. So I have 1 down here, 2, 3, 4, 5. I have 5 C's in my chemical formula, so I have unique 5 carbon environments. Another thing you could check to kind of help you piece things together is still your HDI that we talked about with our mass spec. Again, I just have carbons and oxygens, so I have 5 times 2 plus 2 minus my 10. Again, oxygens are ignored. I'm leaving out nitrogens and halogens because they're not here. So I have 12 minus 10. Which equals 2. Divided by 2 gives me an HDI of 1. So that means I either have a ring or I have some type of alkene or double bond somewhere going on here. So when I make this structure, those are some things I can think about. Some other things I can think about here are the directions of these up-downs. So in my depth 135, my downs correspond to my CH2s. And then my ups correspond to CH3s. Again, the height of the peak has nothing to do with what's going on. Notice that this one is missing from the spectrum. The only thing that ever is missing is a C with 4 things that are attached to it that are not carbons or are quaternary. So that means I probably have a C centralized somewhere that only has other C's, or maybe the oxygen bonded to it and that's it. If I check my parts per million, I'm looking between 200 and 220 to see what would be shifted that far downfield. So if I look here, something between 200 and 220, the only thing that shows up is some type of carbonyl, whether it's an aldehyde or ketone, we can figure that out. Whoops, let me get back down to the right one. So then this probably corresponds to some type of carbonyl with groups attached to it, whether they be hydrogens or they are my CHs in some way, what combination. Some other things I can look at is that I have some very downfield things and very not so downfield things. Another thing to consider here is that if I have 5 C environments, I don't have symmetry. So if I were to add things on here, I have 2 CH2s, 2 CH3s. If I were to do something like this, I would say, okay, I have 5 carbons, I have my oxygen, I have the correct number of hydrogens, and it matches my HDI. The reason this is wrong, though, is because I will highlight for you what C's would be in the same environments. Because of symmetry, I actually would only have 3 in different environments for this structure that I have drawn here. Since I have 5 different environments, I cannot have this much symmetry in my molecule. So what I need to do is figure out where to place this carbonyl to get rid of this symmetry. So what if I switch the location of this carbonyl with the location of this CH2? So now I'll put my CH2 in this position and I'll put my carbonyl in this position. So now I have CH3 groups that are different, CH2 groups that are different, and then I have my quaternary carbon here that's all by itself with no H's on it. This would probably be the best structure to match what's going on because I have the 5 different C groups, I have the very downfield carbonyl, I have the 1 degree of unsaturation due to the alkene in this position, and then I have 2 CH2 groups and 2 CH3 groups. So again, if I were to draw this nicely, to have my 5 carbons and my carbonyl, it would probably look something like this. And this would match the spectrum here best. Again, I don't have symmetry, so I can't use the other option. There's no other option for this, so this would be the best structure for this match. So this concludes how to do carbon NMR. A little easier than proton NMR because you have less to actually inspect, but still interesting to kind of put those pieces together.